Okay. Water molecules that we have discussed last time that bonded natively to the central metal and iron are known as ligands, right? So when the metal ions join with the ligands, it produces complex, right? Most of these complexes are having charge, therefore known as complex ions. Let's say the number of dative covalent bonds are called the coordination number. These definitions are important. Copy this one. So we know what are ligands, complexes, and complex ions. Finish writing. Right. That. So remember, there are several ligands, and some ligands are having charge and some are not. For example, water is a ligand without charge. Hydroxide is a ligand with -1 charge. Ammonia is a ligand with no charge. Chloride is a ligand with -1 charge, right? So when you are writing the name, right, the name of these ligands will change. That means water become aqua, hydroxide become hydroxo, ammonia become amine, and chloride become chloro. Copy this one as well. Examples of ligands. What another point. If the ligand is having a negative charge, name ends with O. Hydroxo, chloro, like that. Done. Moving on. Now let's see how they are naming the complex. Look at this. The name of this ligand is hexa aqua iron 2. Hexa aqua iron 2. So hexa means 6. 6 water ligands, aqua. And it's a positive ion, therefore iron 2. 2 is the charge. Is that clear? How to write the name? Hexa aqua iron 2. Similarly, Kaushika, can you tell me the name for this one? H2O 6 3 plus. Okay. What is the name of this one then? Kaushika?
Hexa
Aqua. No, hexa aqua.
aqua and 3.
Yes, very good. Hexa aqua. Continuing, iron 3. Iron 3. Hexa aqua iron 3. Therefore, this is the order, number of ligand, name of the ligand, name of the metal ion, oxidation number of the metal ion. Okay. Then අපි ලියමු topic එක naming complex ions. The naming complexes. And the first you have to write the order. So we have 1, 2, 3, 4 steps. Now, first you have to write the number of ligands, name of the ligand, name of the metal ion, and the oxidation number of the metal ion. Step number 5. Write down. If the overall charge is negative, If the overall charge is negative, Latin name of the metal is used. Latin name of the metal is used. Latin name of the metal is used. Latin name of the metal is used along with the 8. ATE. Latin name of the metal is used along with 8. ATE. For example, මේ බලන්න ferrate. Tetrachloroferrate. Right. Last point, sixth one. If there are two different ligands, if there are two different ligands, they appear in the alphabetic order. They appear in the alphabetic order. Right. Here you have ammonia and water. So ammonia amine, water aqua. So both starting with A, but M comes before Q. Therefore, amine comes first. So the name is tetraamine. Tetra means 4. Amines, ammonia. Diaqua, copper 2. Okay. I hope this is clear. Then let's copy these 3. May I copy these 4. Okay, finish up. Examples. අපි මේවා name කරන්න බලමු. Sorry. Right. මෙන්න මේ තුන් දෙනාගේ නම් ලියන්න බලන්න. This one, and this one. Latushan, what is the name of the first one? Name of the first one? Latushan? Kianaban, what is the name of the first one? Hexa aqua chromium 3. Very good. Hexa for 6. Aqua, chromium, 3. Hexa, aqua, chromium, 3. Nivesh, second one. Kaushika, name of the second one. You have aqua complex and hydroxo complex. Ola 3. Try aqua, try hydroxo, chromium, 3. Okay, last one. Who can name the last one? Balam, according to the last step and the before last. හරි. මොකද්ද නම? What is the name there? Now you have 6 OH. So hexa hydroxo make a chromate 3. Hexahydroxochromate 3. That's the name. Oh, I am sharing the screen. Can't you see the screen? My goodness. Up to now, we are sharing the screen. Hands up those who can't see the screen. Only one. Right. Done. Okay, let's answer to these 2 questions as well. So this is page number 188. Checkpoint 1 and 2. Okay. Explain why methane molecule will not act as a ligand, because methane has no lone pair. Right. So we learned that anion molecule that are able to donate a pair of electron to form a covalent bond as the ligands, but methane is not able to donate a lone pair of electron because it has no lone pair. That's the reason. Next one, explain why the first product is complex, but the second, product is complex, but not a complex ion. It is a complex because it has two different ligands. Altogether, it has 6 ligands, right? But it is not a complex ion because it has no charge. Simple. It's readily fit to the definition. Moving on. This is very important part, how these transition metal complexes get their color, right? Okay, color of the complexes. Okay, write the topic, origin of color in complexes. Right. Okay. Origin of the color in the complexes is very important topic, right? Right. Okay. So first of all, we have to have good explanation about this thing. Again, you have to by heart this color formation, right? But we have to consider the following concept. That means number one is electromagnetic spectrum that you are already learning from the school, even even in the physics, right? And then similarly the color, energy and the wavelength, that is comes under visible light, right? And then finally how this color is related to the electronic configuration of transition metal ions, right? Okay. Now, this is the electromagnetic spectrum. You know this, right? And what we need is the visible range. Right? So you know that as the frequency increases, wavelength decrease, right? So here to here, the wavelength decreasing and the frequency increasing. So the violet color will be having higher frequency and lower wavelength. That's how it goes. Right? Okay. And the next term, color wheel. This this is the color wheel that you should know, right? In the exam, you won't be getting the color wheel. Therefore, you should find a method to work out the color wheel. So what I am doing is, I'm just splitting 1, 2, 3, 4, this manner. Then rainbow colors. R and 2 become R, that's it. So 2 R's are there. That's all you have to do. So this is the color wheel. Okay. And the next I will give time to write, so don't worry. So next important one is how to identify the complementary colors. So in the color wheel, colors are opposite to each other are known as complementary colors. So yellow and violet, orange and indigo, red, blue and red, green are complementary colors. Okay. So just tell me whether you have any doubts in considering the complementary colors and color wheel and electromagnetic spectrum, under that the visible range. Do you have any doubt? Let's start then. Okay. First copy this part. Then draw my sketch diagram that is for the color wheel. How the color wheel looks like. Color wheel, color wheel. Next topic is color wheel and draw my beautiful diagram that represent the colors. Okay. Next one, complementary colors. Complementary colors. Colors opposite to each other. Colors opposite to each other. So, why are we talking about this complementary colors, especially when transition metal complexes? When white light pass through a transition metal complex or solution of transition metal complex, it absorbs some colors and some amount of light will emit, right? So the color complementary to the absorbed color will be emitted. Is that clear? Is that clear? So let's say you have transition metal solution in this manner. You have transition metal solution and you are sending the white light. This is not white light. Right? So if it absorbs this orange color, right? So the emitted color will be indigo. So you can see the indigo color. That's how it goes. Clear or not? Right? I think that particular part you have to write, right? Any doubts in this case? Vanhevani, Latushan, Rukaya, Nivesh, Haushika, is this clear? How this complementary color thing work and why it is useful when we are determining the color of transition metal lines? Right. This part. Copy this one. I'll repeat again. Complex will absorb some colors and colors complement to the absorbed color can be seen. Now, still, this is not the full process, right? You need some time to explain this, so just wait. Right. Okay. Then write the topic is origin of color. No? Okay. Then write the separate paragraph. right? Separate paragraph, and this is what you have to by heart for the exam, right? Ligand cause, ligand cause d orbitals to split into two different energy levels. Ligand cause d orbitals to split into two different energy levels. Now, we know there are 5d orbitals. They are like this. That means all of they are having the same energies, right? But because of the ligands, these d orbitals will be split into two different energy levels. That means one lower and one higher, like this. Okay, copy this diagram. So this happens due to the ligands. So when the ligand comes, right, split the energy levels into two. Ligand cause d orbitals to split into two different energy levels like this. Okay. ඊට පස්සේ for this to happen ළමයි, the next step to happen, there should be vacant one, right? There should be vacant orbital in the higher level. Okay, so in the first step you wrote ligand cause d orbitals to split into two different energy levels, right? And then the next point, electron in the lower level, an electron in the lower level will absorb energy from the visible light. An electron in the lower level will absorb energy from the visible light and move to a higher level. That's what I told you, that there should be empty orbitals, right? Okay. So the second point is electron in the lower level will absorb energy from the visible light and move to a higher level. And the last point, color complementary to the absorbed color complementary to the absorbed color can be seen. Color complementary to the absorbed color can be seen. Now is that clear? I'll repeat the entire steps again from the beginning. Ligand cause d orbitals to split into two different energy levels. Electron in the lower level will absorb energy from the visible light and move to a higher level. Color complementary to the absorbed color can be seen. Okay? Right. Done. Now, that explains why zinc cannot behave this case, because now behave like transition because its d orbital is complete, d orbitals are completely filled. Therefore, there will be no way of transferring electron from one d orbital to another. So this electron transfer is known as dd transition. dd transition. So here it's not possible even in the scandium, right? It's not possible because there are no d electrons. Okay. So this is what you have to by heart when you are writing how the color is formed, right? And here the second diagram. After that, you have to draw this one. And note that this electron has moved by absorbing energy from the visible light. Okay, copy this one. Okay, finish writing lamai. Sorry, finish copying me. I have to finish the class early today. I have to finish by 6. I'll cover it in the next day. Remind me. So the process that is known as that formation color DD transition will somewhat similar to what has happened in the flame test. But it's not the same, remember. That is emission spectra. This is absorption spectra, right? So let's say flame test. Don't get jumbled with that, because now some of you are doing unit 1, I mean the A's, no? So you will be getting some confusion with this transition metal colors. Transition metal colors. So here what has happened in the flame test, when you heat, electrons will absorb energy and move to higher level. So at higher stages, now here if it's the ground state, this is the higher state. So they are unstable, they will fall back to the ground state while releasing energy. Releasing energy as visible light. So releasing energy. If this energy is in the visible range, you can see the color. But here what will happen? These complexes will absorb. And complementary color will be emit. Therefore, transition metal colors based on emission spectra. So, right? No, sorry, actually not the emission thing, right? Absorb and you will be seeing the complementary color. Complementary color will be seen. There will be no emission, sorry. Complementary color can be seen. Emission is here. Now, is this too clear? How the transition metal colors are different from the flame test color? Now, if it absorb yellow, on the banner, then there's a question, if it absorb yellow, go back to the color wheel, right? Complementary color. Complementary color. If it absorb yellow, you can see the purple color. If it absorb purple color, you can see the yellow color. Right? Clear? Now, you might have seen in some farms, especially where they have fruits, they are covering these fruits with special type colored polythenes, right? In order to absorb that particular color. Same thing. Right. Similar task. Okay, we'll answer these 2 checkpoints. Checkpoint 1 and 2. Answer these 2 checkpoints. Now the question says Fe3 plus yellow. Which part of the electromagnet is absorbed by these colors? Look at yellow. Obviously, it is purple color. So the purple color is here. So somewhere around 400 nanometers. And then the next question, why aluminium 3 plus ions are colorless? Right? Because simple, because no DD transition taking place. Right? That means the color occurs due to this DD transition, no? Electron in the lower level will absorb energy from the visible light and move to higher level. So this process will not be happen. Therefore, aluminium ions are colorless. Moving on. Predicting the shapes of complexes. The shapes, complexes too are having shapes, but the shape is simply, right, follow the electron pair repulsion theory. Based on electron pair repulsion theory, we can determine the shape, right? So there are three most common shapes, that is octahedral, tetrahedral, and linear, right? Octahedral, tetrahedral, and linear, right? So octahedral means 6 ligands. Similarly, we can call it as 6 bonds. So when there are 6 bonds, those who have done the AS, you should remember that 6 bond, the shape is octahedral, bond angle is 90. Then 4 bonds, tetrahedral, bond angle is 109.5. 2, it's linear, bond angle is 180. That's how it goes. Let's copy this. Finish copy. With the example. So what we learned was shapes and yes, shapes of the complexes. It goes according to the electron pair repulsion theory, and number of ligands can be number of ligands. That means like number of ligands. So you can say the number of dative covalent bonds you can consider as the bond pairs. Based on that, you can come to the shape 6 bond pairs. So the 6 donations make it octahedral. 4 donated pairs tetrahedral. 2 donated pairs linear. And the shape when it comes to octahedral, bond angle 90, tetrahedral 109.5, linear 180. An example, everything are given there. Right. So with this, I'm going to stop for today. And I'll be coming tomorrow. So I hope to see you tomorrow morning. God bless you, Lamai then. If there's any doubt, don't forget to ask, right? I will be answer it soon as possible. Okay then. God bless you, Lamai.